Hello everyone. Let's look into one more example for crosstalk glitch. So this case is goes something like this. Let me describe the case over here. So this particular aggressor driver input, which is marked over here, is now switching from logic 0 to logic 1. In contrast to the case that we saw earlier. In this case, the input of this particular aggressor is switching from logic 0 to logic 1. Okay, and the second assumption is that the victim driver input, that is at steady state logic 0, that is this one. The victim driver input is at steady state logic 0. So what can we expect when it is at logic 0? Obviously the output of the inverter will be logic 1. Okay, so here it's logic 1, here it's logic 1. When we say logic 1, it basically says that this particular capacitor are charged to its full voltage. So they are completely charged, and you see a waveform which is at logic 1. Basically this particular net is constant, is at a steady state value logic 1. Okay. Next, what we'll do is now we'll take the input of this particular aggressor driver and switch it from logic 0 to logic 1, and simultaneously see what happens to the aggressor output and what happens to the victim over here. Okay, so now the input is switching from logic 0 to logic 1, and similarly the output will be switching from logic 1 to logic 0. So now when we say it is switching from logic 1 to logic 0, what does that mean? It means that this particular tap is now open in a reverse way, and all the charges that is being stored at the capacitance at this node, they're all getting discharged through this particular inverter. Now what is happening is, let's try to consider this particular capacitance or this particular coupling capacitance as a reverse bucket with a hole over here. Initially the bucket was in this direction with a hole over here. In this case the bucket is the same, it's in the reverse, it's placed in the reverse direction, and there is a hole at this point. Okay, so while this particular aggressor, this particular node, while all the other capacitance on this node try to discharge, let's see what happens. So now this particular node is now completely discharged. Okay, so in the process of discharging, in this period when all the capacitance at this point are getting discharged, this particular node sees this particular bucket which is reverse placed, and it sees a hole in this particular bucket. Okay, so now what is happening is, this particular victim which was completely charged to logic 1, it gets discharged to this particular through this particular inverter for some time, and then again gets charged to its logic 1. So here is what is happening. So once the output of this particular inverter is switching from logic 1 to logic 0, basically all the capacitances over here which is seen by node A are all getting discharged through this particular inverter. And in this process, since this is a bucket which is completely filled, but it's in a reverse direction, and you see a hole at this bucket, so the charges which are present over here, they also try to discharge through this leaky bucket, and then through this inverter, because this inverter is strong enough to take this charge and discharge it. Okay, so this is the way you see a reverse glitch kind of thing. It's called as fall glitch because it's at logic 1 and it's falling to some other potential which is less than logic 1, hence it's called as a fall glitch. Let's talk about that in some time from now, but this is what is happening when you see a scenario over here. So the scenario is exactly the same as the before, it's just that the bucket is now reverse placed, and whatever the water that was filled in this buckets, those are now getting leaked through this particular capacitor, through this particular bucket, and through this particular inverter. They are getting leaked for a moment, they are getting momentarily discharged, and then again it comes back to the original potential, which is logic 1. Now again, two things we have to understand over here. One is, what is the tolerable value of this fall glitch, or what should be tolerable value of this particular potential of the voltage of this glitch, and second, how it comes back and again charges to logic 1. These two things we have to see. And again, as we saw in the previous lecture, we will again open up this particular inverter. This particular inverter will open up, and first of all, this is called as a fall glitch, and the reason is quite obvious, that it is falling from logic 1 voltage to some potential which is less than logic 1. So that's why it's called as a fall glitch. Now let's try to understand the second part, where we have to see why this particular capacitor, why this particular node which was momentarily discharged again charges back to logic 1. Okay, let's look into that now. So again, we'll follow the same procedure. We will open up this particular inverter and see what is the scenario now. Okay, this is pretty interesting. So this particular inverter again has got a PMOS at the top and NMOS at the bottom, and when we give a logic 0 at the input of this particular inverter, now the situation is completely reverse. So the NMOS will be off because it sees a logic 0 at the input, and the PMOS will be on because it sees a logic 0 at the input. So PMOS turns on, NMOS turns off. So now your PMOS is on over here and your NMOS is off. So we can follow this same modeling strategy that we followed for an inverter. That is, whenever when some transistor is on, you can replace that by a resistor, and when something is on, you can replace that by an open switch. So let's do that. Let's try to model this particular inverter in the same fashion we did in the last video, and see what we get over here. Okay, so we have replaced by the on transistor by a resistor, and we replaced the off transistor by a open switch. So now you see this, whatever capacitor that is present over here, you see there is a charging path from the VDD to this particular capacitor, and that's the reason why you see a logic 1 potential at this particular node. So that's pretty simple, that's pretty easy to understand. Now let's see now. So now what we have to see is, what we have to look into is, we have to revise this complete procedure and see how it gets charged back to gets charged to logic 1. Okay, so you have the output of the victim at steady state logic 1. You have the input of the aggressor which is at logic 0. Output of the aggressor is currently at logic 1. Okay, so input of the aggressor now switches from logic 0 to logic 1. In the same way, the output of the aggressor switches from logic 1 to logic 0. So rather than switching, let us say the capacitors that is present at node A are getting discharged through this particular inverter. Okay, and in this process you see the charges that are present on this node, they also get discharged through this particular path. They have a path through this coupling capacitance, and they try to discharge through this path, and that's why you see a dip in the potential over here. Now when this particular aggressor comes back to a constant steady voltage, basically there is no switching activity after this point, so the aggressor is at steady state voltage which is at logic 0. So since there is now no switching happening, now whether this particular glitch or whether this particular drop in the voltage has to come back to the logic 1, or it has to go back to logic 0. So who will decide that? Again, in the same way, it will be decided as it was decided in the past by the on resistance of the NMOS transistor. Here it will be decided by the on resistance of the PMOS inverter, of the PMOS transistor. So basically, the lower the resistance, the higher the drive strength of this particular inverter, and the higher the chances of this particular glitch to come back to logic 1. Okay, so that is what has been the observation in the past. So let's assume that the on resistance is very high, the on resistance is very low. If the on resistance is very low, if you see this particular glitch now it down now this particular VDD will be continuously supplying the charge, will make sure that this particular capacitor again retains back its logic 1 voltage. So this will be charging the capacitance. If you see over here, it's charging, it's again charging, and then finally it goes back to logic 1 voltage. So this additional charge that gets lost because of this coupling capacitance through this particular inverter is again restored by the resistance, by the least resistance of this PMOS over here. So since the PMOS is of low resistance, there is a high possibility that the glitch charge is getting restored again, and you see a logic 1 voltage over here. Had this on resistance had been very low, oh sorry, have the resistance had been very high, in that case there was a very high possibility that this particular glitch will go down and settle over here somewhere at zero potential, and at the output you see a logic 1, which is again a potential failure, or it's a functionality failure of the circuit. Okay, so this was one more example that we tried to explain how does the glitch behaves and all those things. Now we have to move into even deeper explanation of the glitch. For example, we have to look how tolerable this glitch is. So in that case we have to study the concept of noise margin and so on. We have to find out the way. So one way we found out to avoid the glitch is to make this resistance as low as possible. But there are other implications, or there are other disadvantages of doing that. We will also look into that, and again there are some other factors on which this particular glitch depends upon, whether this is a potentially hazardous glitch or whether it's a safe glitch. So there are some other factors on which there are some other factors of the glitch that decides whether how safe or how tolerable the glitch is. So let's try to start from all those things in the next video. Thank you.